Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Good morning, students. Today we are going to start with the general characteristics of some important compounds of alkali metals. We have actually studied in details, not exact quite details, but we have studied the chemical properties of alkali metals, how their compounds, different type of whether carbonates, oxide, hydroxides, bicarbonates, sulfates, how they are formed or what are their characteristic properties. We will just be summarizing few important chemical compounds and what are their properties, so that we can do. These are very important points, and these are summarized here in this under this subtopic. So general characteristic means this very important chemical compounds of alkali metals, that particularly will focusing on some oxides, some hydroxides, halides, and nitrates mostly. So because they are high electropositive character, and we know alkali metals, they have very high electropositive character, and that is why their compounds are mostly ionic. Though some of these compounds have quite a significant covalent character, but they are mainly the ionic compounds, with some compounds having some covalent character as well. And that why how this covalent character, that we can decide according to the Fajans rule. So let us look into the oxides and hydroxides. And about the oxides, what we have studied, that the lithium usually forms normal oxide. Normal oxide means where oxygen's oxidation number is -2, and the lithium, its oxidation number will be anyway +1. For all the metals, it will be +1, because alkali metals, their oxidation number is always going to be +1 in their compounds, all of their compounds. And some of the peroxides are also formed. Lithium also forms some peroxides, but proportionally its concentration is very less, its presence is very less. So lithium majorly forms normal oxide, and major product of sodium with oxygen, or after reaction with oxygen, is the sodium peroxide. However, we also see some oxide and some superoxide. And potassium, rubidium, and the cesium, they mostly form superoxides. However, for potassium, we also see a trace amount of peroxide. So usually what we have to remember is lithium, major product of lithium with oxygen is the normal oxide, which chemical formula is Li2O. The sodium, it forms peroxide, Na2O, and potassium, rubidium, and cesium, they form superoxide with the formula MO2. And now what we know, what I have explained earlier, that the normal oxide is diamagnetic in nature, when peroxide is diamagnetic in nature, but superoxide, sorry, normal oxide and peroxides, they are diamagnetic in nature. However, superoxide is paramagnetic in nature. Now, how this magnetic behavior is changed and how it is determined, we will see a bit later. And normally oxide, if you look at the normal oxide, it means oxygen in -2 oxidation state. It means that oxygen atom, a single oxygen atom, it accepts 2 electrons, so it will become normal oxide, O2 minus. O2 minus, now if you look at all the orbitals, if you like write the electronic configuration of oxygen O2 minus, oxygen anion, oxide anion, then you will see that all the electrons are paired up, because if you look at the electronic 1s2, 2s2, 2p6, this will how be the this is how what is the electronic configuration of mm, uh, this oxide anion, or 2 minus anion. And the oxygen, we know 1s2, 2s2, 2p4. So there are 8 electrons. However, in the oxide, in oxygen atom, there are 8 electrons, and oxide, there will be 10 electrons. So 1s2, 2s2, 4 electrons, then 2p6, 4 plus 6, 10 electrons. And now we see all the electrons in all the orbitals, they are paired up, so they are diamagnetic in nature. And in the metal oxide, it is a metal is having +1 charge, so metal, all the electrons in the metal ion is also paired up. So what do we get? We get the entire lithium oxide, it's a diamagnetic in nature. So diamagnetic means no unpaired electrons. Now, if you look at the peroxide, for to look into the peroxide and its magnetic nature, we will have to go to the, because this is peroxide, it is O2 2 minus. Then here we will have to look at the molecular orbital diagram of oxygen, and then how the extra 2 electrons that comes to form O2 2 minus, how those, where in which orbitals those electrons are filled. And similarly, O2 single minus in the case of superoxide, that single minus O2 single minus, where that electron has gone, and based on that we can determine whether this will be diamagnetic or paramagnetic. So normal oxide, that we can understand very easily that they are diamagnetic. For peroxide and superoxide, I will be explaining in the next slide with the molecular orbital picture, so that we will see a bit later. Let us look into the other points. The increasing stability of peroxides or superoxides at the size of metal ion increases is due to the stabilization of large anion by larger cation through lattice energy effects. This I have explained earlier. These oxides are easily hydrolyzed by water to form hydroxides. So oxides, all the oxides, whether they are normal oxide of lithium or peroxide of sodium or superoxides of other alkali metals, heavier alkali metals, what do we did? All these oxides, all the three forms of oxide, when they react with water, they forms hydroxides, means they form alkali, and so we get the NaOH or LiOH or similarly MOH kind of compounds. So these oxides easily hydrolyzed by water to form hydroxides, they form alkalis, and that is why they are alkali metals. The oxides and the peroxides are colorless. So here we should remember oxides and peroxides are colorless. Usually all the electrons are diamagnetic, and we have seen earlier as well that the diamag. So if they are diamagnetic, usually what will, there will be no electron, the excitation of these electrons usually, if you excite these electrons, you have to cross a larger barrier, or not the barrier, you can say, means you have to provide larger energy. The gap of the next excited state and this ground state is too high, so that we do not see color of this on oxides and hydroxides. So means they do not show any color. So they are colorless when they are in pure form, and but the superoxides are yellow or orange in color. So they yellow or yellow orange in color, and why it is because the superoxides, there is one unpaired electron, and the next excited state is not that high in energy. So the superior the superoxides are paramagnetic, whereas oxides and peroxides are diamagnetic. And how this superoxides are paramagnetic and others are diamagnetic. So oxides I have explained. Let us look into the peroxides and superoxides. Before going look into this peroxides and superoxides, their molecular orbital picture, let us look into the molecular orbital picture of oxygen molecule O2. And what we know, oxygen molecule itself, it's a paramagnetic in nature. O2 is paramagnetic in nature, and this is what one behavior this we get, and this, it was explained by molecular orbital theory. This valence bond theory fails to explain the paramagnetic nature of oxygen molecule, and that is why we needed another theory to explain such behavior, and the molecular orbital theory successfully explains it. And what the molecular orbital theory we have seen, the basic idea is all the atomic orbitals they take part in, they actually combine together. There is a linear combination of atomic orbitals we talk about. Means all the atomic orbitals they combine with each other to form molecular orbitals, and the similar or atomic orbitals, means atomic orbitals with the same energy and same symmetry, they combine to form molecular orbitals. And that is why 1s of one oxygen will be overlapping with the 1s of another oxygen atom. So 1s. So what will happen, one bonding and one anti-bonding orbitals will be formed, and that we call sigma 1s and sigma 1s star 1s. Sigma 1s is bonding orbital, and sigma star 1s is anti-bonding orbital. So similarly, all the atomic orbitals they combine with each other, linear combination between them happens, and after that what we see, a formation of bonding orbital and anti-bonding orbitals. Anti-bonding orbitals are represented as a star sign, and bonding orbitals we do not show any star. And Another thing is if the electron is there in the bonding orbital, we see the molecule is now more stabilized. And if the electron is in the anti-bonding orbital, then we see that this because of the presence of electrons in anti-bonding orbitals, we see some certain destabilization. And why destabilization? If you look at this, just look at these two orbitals, 2s and 2s, they combine to form sigma 2s and sigma star 2s. If the electrons are going here, you can see this what 2s sigma 2s is lower in energy than the atomic orbitals. So if electrons are going into the bonding orbital, so the energy of the system will be decreasing, and it will be decreased by 2 into this amount because 2 electrons are there in this orbital. If one electron is there, so it will be 1 into that electrons. Now, if you look at this gap, if the electrons are now being put into the anti-bonding orbitals, means whatever the stabilization that was gained by putting electrons into the bonding orbitals, now you have put electrons in anti-bonding orbitals by almost same extent or slightly more. This destabilization happens. So this system is now not stable. So these things we have seen in nature. Now look into the molecular orbital picture of oxygen again. So 1s2 sigma 1s2 and sigma star 1s2, each molecular orbitals also occupy maximum 2 electrons. So that is why 1 is sigma 1s2 sigma star 1s2, those two electrons were there. Now we'll come to sigma 2s and sigma star 2s. So now here you can see both bonding and anti-bonding orbitals of type sigma 2s and sigma star 2s, they also contain two electrons each. Now we on that energy scale, what we get, the next orbital molecular orbital is sigma 2pz. Please remember that these orbitals are not there in the molecular oxygen. These are orbitals of oxygen atoms, separate oxygen atoms. In actual orbitals that we can imagine and we hope to be available in the oxygen molecules are these. So sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, then pi 2px, pi 2py, then pi star 2px, pi star 2py, sigma star 2pz. This is how these are molecular orbitals are there and in their increasing energy, and this is the order. So now electrons will be here. Total electrons will be the 16 electron in the oxygen molecule. So 16 electrons, so 4 electrons were there in the 1s type orbitals. So now 4 electrons here for sigma 2s, 4, 4, 8, plus 2 here, 10, 4, 14, and 2 electrons now will be in the pi star 2px and pi star 2py because these are degenerate orbitals, and degenerate orbitals have same energy. So electrons will be now put, one electron each will be put in them according to Hundsul. They are degenerate orbitals. So first electrons will be singly filled, and they are singly filled. Now the pairing of these electrons will happen if there are extra electrons. So what happens is the oxygen molecule, we see there are two unpaired electrons. So oxygen is paramagnetic in nature. Now, if we look at the peroxide means two extra electron is there than the oxygen molecule, and that is why it has two negative charge, two minus charge. And those two electrons, where will put those two electrons? Now, those two electrons will be coming into this anti-bonding orbitals itself. So these electrons will be paired up. So there will be one electron with the opposite spin in this orbital, one electron with the opposite spin in this orbital. So pi star 2p pi star 2px2 and pi star 2py2. This will be the final, the last valence cell electronic configuration of O2 minus, the last outermost cell electronic configuration. Cell, we cannot say outermost orbital, their configuration, and this will be the configuration. And so what we see, all the electrons are now paired up in the superoxide. Rest of all the electrons will be, their pairing will be the same. Only the change that we see, the two extra electrons will now be occupying these two anti-bonding orbital. So now two electrons have gone into the anti-bonding orbital. So we will see also the change in the bond order. So the superoxides, its bond order is 1 because oxygen's bond order is 2. 2 means the double bond, and the superoxide, if you look at it's a oxygen single bond, and there will be two negative charge on both the oxygen. If you see anywhere, all the books it shows. And why it is? Because now two extra electrons has come to this anti-bonding orbitals, and if you look at all the difference, bonding electrons minus anti-bonding electrons divided by 2 in the peroxide, you will get the value will be 1. So to look here, so 2, 2, 4 and 4, 8, and minus, and 2 electrons for the one sigma is 1s 2. So a 10 electrons and the 6 electrons will, rest of the 6 electrons will be in the anti-bonding orbital. So 6, the 10 minus 6 is 4 divided by 2. This is what we say, bonding orbitals minus anti-bonding orbital. Bonding electrons minus anti-bonding electrons divided by 2. So 4 divided by 2, the bond order is 2 for oxygen. Now if we put 2 extra electrons into these orbitals, so what will the anti-bonding electrons will be 8. So 10 minus 8 divided by 2 will be the bond order. 10 minus 2 divided by 2, 1 is the bond order in the peroxide. And now we see all the electrons are paired up. So peroxide is having no unpaired electrons, so it is diamagnetic in nature. In the case of superoxide, superoxide has only one extra charge, one negative charge. Means if in O2 molecule, if you add only one electron, you will find the superoxide. So that one electron you can put either into this or this. It doesn't matter because they are degenerate orbitals and electrons are indistinguishable. So anywhere you can put them. Indistinguishable means you cannot recognize which electrons and which orbitals as well. Though we have given some symmetry to understand the chemistry of the physics behind it, but the thing is, in reality, in the practical sense, you may not understand what are these orbitals, because anywhere if you can just take this axis is x-axis, another axis y, you can just change this convention, and so the x of p pi star 2px will become pi star 2py. So anyway, it doesn't matter. So in any of them, you can put one extra electron, and one electron. Suppose I put one extra electron into this in the superoxide. So this electron is one unpaired electron will be already there in the superoxide. So because of that one paired electron, the superoxide is paramagnetic in nature. And so what we see, one unpaired electron, and why unpaired electrons up to here at this level, we see the same electron configuration as to the oxygen molecule. However, here at this level, we see this pi star 2px1. I have put only one electron into pi star 2px and two electrons into pi star 2py. So here, so what we see, one unpaired electron is here, and because of this unpaired electron, superoxide is paramagnetic in nature. And this answers this question. So why superoxides are paramagnetic? And this is why, because superoxide is because of one unpaired electron in pi star 2p molecular orbital. And with the molecular orbital picture, I hope it is more clear. The hydroxides which are obtained by the reaction of the oxides with water are all white crystalline solids. They are all white crystalline solids. What they are, all the hydroxides are which were obtained by the hydrolysis of oxides of alkali metals. Oxides means all the peroxide, superoxide, and the normal oxides. They are all white crystalline solids. The alkali metal hydroxides are the strongest of all bases and dissolve freely in water, and that we know, other than lithium hydroxide, all the alkali metal hydroxides are readily dissolved in water, and they are very strong bases. And so the and the evolution of heat on so when we dissolve them in water, what we see the dissolution of heat, because their dissolution is very fast. It is favorable. Dissolution is favorable, which means energetically favorable means what, the energy will be released, and that energy will be dissipated in the to the system. It will go surrounding, will go into the surrounding, and so that by that much amount the energy will be released, and the energy of the entire system will be decreased. And so this is very favorable. Dissolution of alkali metal hydroxides is favorable, and that is exothermic in nature. So now looking into the halides. All the alkali metal halides means we have seen it is MX type, and MXX could be the halides. Usually represents any, all the halides have simple X, and X means fluorine, chlorine, bromine, iodine. Here it will be chloride, bromide, iodide, because it is X represents a negative charge here on X minus. It is M plus and X minus. So only X if we represent here in this form FCl, Bri minus. But if you separate these ions, so it is M plus and X minus, then in that case X will be F minus, Cl minus, Br minus, I minus. They are all high melting colorless crystalline solids, and NaCl that mostly you have seen. This is a salt that we use in daily life, and it is colorless, and it has very high melting point, and the crystalline solid. They can be prepared, these halides. They are prepared by using oxides or hydroxides or even carbonates of alkali metals. What you do, you use oxide or hydroxide or carbonates, and they just react with any hydrohalic acid. Hydrohalic acid means hydrochloric acid. You remember chloric. Halic is here the chloric. HCl, hydrochloric acid, hydroiodic acid, hydrobromic acid, hydrofluoric acid, HF, hydroiodic HI, hydrobromic HBr. So hydrohalic, the common name we can write for the HX. So if these compounds, oxides of alkali metals or the hydroxides of alkali metals or the carbonate of alkali metals, when they react with HX, which is an acid, what we see the formation of the salt MX. So for example, NaO2, when it reacts with HCl, it will form NaCl, and NaCl, the salt that we know. All of these halides have high negative enthalpies of formation. High negative enthalpies of formation means these reactions are exothermic in nature. It means the energy will be released during the formation of all these halides, and energy release of energy means delta H formation will be negative. The formation this we represent as delta F H naught values for, and H naught means in the standard state, so that all the reactants are in their standard physical state and the standard conditions we know. I have explained earlier. It's a If it is a gaseous state, any of the reactant is the gaseous state, so it must be at the 1 bar pressure. If the temperature should be around 25 degrees, the room temperature that we usually consider, and if it is in the solution form, its concentration is should be 1 molar. These are standard state conditions. So when all the reactants are in the standard state and the product that is formed is also obtained in the standard state, whatever the energy that is released, that we represent as delta F H naught values. This value for fluoride becomes less negative as we go down the group. So for fluoride, what happens if we look at LiF, NaF, KF, RBF, CSF? So for these are all fluorides of lithium. As just I am saying, the lithium fluoride, alkali metals fluoride. Now delta S value fluoride, what happens? The alkali metal fluorides, it becomes less negative. And why it becomes less negative? Because it's a lattice energy decreases. And lattice energy, why it decreases? Because you see here the lattice energy, the size mismatch happens, and because of the size mismatch, the coordination number is affected. So coordination, if the larger size metal ion comes and fluoride is a smaller size, you will not get any optimum number of uh, cations surrounded by the around the surrounding the fluoride ions, because fluoride is very smaller in size. So what will happen, as the size increase, the less and lesser number of the cations will be surrounding fluoride ions. So usually what happens, so if their number is decreasing, so delta F H naught, the value will be also be decreasing, because this attractive interaction cation and anion, so lattice energy will be more, and that we see that this value will be more negative. So as we go down the group, if since lattice energy is decreasing because of the coordination effect, and so there the delta F naught value for the fluorides of alkali metals, it decreases. However, for the other halides like chloride, bromide, and iodide, we see the reverse order is true. Reverse order is true means here the chloride is much larger in size than the fluoride, and similarly bromide and iodide. So the coordination number is what we'll see. The coordination number is better accommodated with the larger size cations, and so what we see, the reverse order is true. In the reverse order, lattice energy changes. So if you look at the examples for the chlorides, if I look at the Cl, cesium chloride, then rubidium chloride, then potassium chloride, then sodium chloride, then the lithium chloride. So what we will see, the lattice energy will be from the cesium chloride to the lithium chloride, it will be decreasing, and so the delta F H naught value will be also decreasing. So for a given metal, delta F H naught always becomes less negative from fluoride to iodide. However, this is very important point. Sometimes we see that this is contrast to this, but this is not that. So what means, if you choose any alkali metal, suppose I choose whether I choose a lithium and consider lithium fluoride, lithium chloride, lithium bromide, or lithium iodide, or the cesium chloride, cesium chloride, cesium bromide, cesium iodide, what we see for any chosen metal, if you increase the size of fluorine and bromine, this is here what wins is it the in the iodide is the size of, again, the fluoride. What happens with the size, other effect what is happening, the distance between two ions is also increasing, and with the increasing distance, what happens? The interaction energy decreases. And though the coordination number is better accommodated, but the thing is that each interaction is decreasing. So even if the coordination number is high, what happens for a particular metal? We see for the particularly in the lithium, I am saying if you go down the group, so it happens that this interaction energy decreases because the anion size is increasing. And anion with the increasing anion size, what happens? The distance between the lithium cation and larger anion means iodide will be increasing. The bromide, it will be lesser, and then chloride, lithium chloride is lesser, unless for the lithium chloride. However, in the case of other cases, the other effect will be more dominating. So we see the same trend for all the alkali metals from fluoride to iodide. Usually, what we see, delta F H naught is always more negative, is always more stable product we will get from fluoride to iodide. The melting and boiling points always follow the trend, and that is why since this we see all the alkali metals, the melting and boiling point for fluoride is more than the chloride, then bromide, then iodide, because for any alkali metals, like if the LiF, LiCl, LiBr, Li, this is the trend. Again, similar for the NiF, NiCl, NiBr, NiI, the same trend, because delta F naught is the formation of enthalpy of formation in the standard state is decreasing, and so it means it is decreasing. Why? Because the lattice energy is somewhere it is decreasing in that order, and so what we see, the boiling and melting point also decreases in this order, and boiling point and melting point for chloride, for any metal fluoride, will be maximum, and least for the iodide. All these halides except a few are usually soluble in water, and means what all the halides of alkali metals, they are soluble in water. And NaCl, that we know, it's usually dissolved in water, very readily dissolved in water, and that is why we put salt in our food to enhance the taste. If it was not dissolved in water, there is no use of adding salt while cooking the food. And so these examples that we know, so all these halides were what? There is readily dissolved in water. There are, however, there are some exceptions, and these exceptions, this LiF, the lithium fluoride, which is not dissolved, its solubility is very less in the water, and this is why it is, because we have seen the dissolution depends on two things. One thing is the lattice energy, and another thing the hydration energy. If the hydration energy is dominating and lattice energy is not the dominating factor, hydration energy is the dominating factor, then any salt will be readily dissolved in water. And if the lattice energy will be dominating factor, means its value is more than the hydration energy, so what we see, that it will not be dissolved in water. So what happens usually, the lithium chloride, for the lithium chloride, its lattice energy is more, and for lithium, we have seen the hydration energy is also more, and fluoride is a smaller anion, so for the fluoride also the hydration energy will be more. But the thing is, the lattice energy in the case of LiF wins over the hydration energy. So lattice energy is more, and so we need to, and the hydration energy is less. So the energy released, the energy released is less in amount than the energy that is required to break the lattice. And so what happens, the LiF is, it is LiF solubility is very low in water. However, if you look at the another extreme case, CSI, it's a anion is also largest in the size, and cation is also largest in the size. These are smallest cation and anion. And here what we see, in this case, lattice energy is also less, and the hydration energy is also less, because cation and anion both are largest, they're in size. But here again, what happens? They are both less, but again, the hydration energy, its amount, the value is much lesser than the ionic, than the lattice energy in this case as well. And so what happens, this again, this region that we say here is the CSI is due to a smaller hydration enthalpy of its ion. So what in the case of LiF, the lattice energy is much too high than the hydration energy. So lattice energy is the dominating factor, it becomes too high. In the case of CSI, what happens? The hydration energy becomes too low. The lattice energy, though it is lesser than the LIF, but that has not decreased to the extent the way the hydration energy has decreased. So hydration energy also decreases, lattice energy also decreases. Decrease in lattice energy is not the dominating factor. Actually, the decrease in hydration energy is the dominating factor here in the case of CSI. So CSI is also very less soluble in water. The other halides of lithium are soluble in ethanol, acetone. So we can see the other halides of lithium, not other alkali metals. The lithium, they are soluble in ethanol, acetol, and acetone and ethyl acetate. These are organic solvents. And what does it mean? And LiCl is also soluble in pyridine. So LiCl is soluble in pyridine. Pyridine is also organic solvent. What is pyridine? So if one CH group of benzene you replace with one nitrogen atom, so it will be the pyridine. One CH of benzene, the pyridine. So pyridine is a liquid. So LiCl is dissolved in liquid, which is LiCl is dissolved in pyridine. Pyridine is also organic solvent that we know. Acetone, ethanol, ethyl acetate, they are all organic solvents. And what we know, the polarity of these organic solvents is less. And the lithium, other ionic compounds of lithium that we know because of the Fajans rule, a smaller size of cation, the covalent character of lithium halides are more, and because this covalent character is more, so the polarity of these lithium halides are less. Why this polarity is less? Because some covalent character has come. So some electron density of the anions will be shifted towards the lithium atom. So it will lithium ion, lithium cation. So it will come into the lithium cation's boundary, the ionic boundary. So some electron density. So what we see, the charge on lithium cation, positive charge will be decreased, and the negative charge on the halides will be decreased. And if the charge on the cation and anion is decreased, so what we need, the dipole is what? The charge into the separation. So charge is less, and so the dipole moment will be less. And also lithium, but we know the lithium size is less, so even the separation is also less. With the less charge value, charge is also less, diminished because of the polarization due to a smaller size lithium cation. And another thing is what? Lithium cation size is also a smaller, so the charge into the separation, and the separation is also for the lithium halides is less. And so what we see, separation is less and the charge is also less. So it means that the dipole moment will be less, because Q into 2L, if you remember the physics class, 2L is the separation between the two charges. When the Q and minus Q, plus Q and minus Q are separated by 2L distance, so dipole moment will be Q into 2L, and Q is the magnitude of any of the charge. Yes. So salts of, now let us remove salts of oxo acids. Oxo acids, first let us understand what is the oxo acids. So if you look at, if you remember some of the acids, their structure, you will see some oxygen, double bond oxygen, an atom, and there is a double bond between that atom and oxygen. And you will also see that there will be OH group associated with the same atom. For example, if you look at the H2SO4, H2SO4 is what? The sulfur is in the middle, and two sulfur oxygen double bonds are there. So H double bond O on one side, S double bond O on the other side, and at the two other sides in the tetrahedral geometry, there will be two OH groups. So what we see on the sulfur atoms, two OH and two double bond O groups, and these double bond O groups are called oxo groups. So two oxo groups are associated. So H2SO4, one can say it's an oxo acid. Similarly, if one can say the HNO3 is also an oxo acid. There are many oxo acids, the HClO4. So there are oxo acids. The carbonic acid H2CO3 is also an oxo acid. And what we see, there is one C double bond O and two COH2 groups, OH twice groups, the hydroxyl groups attached to one carbon atom. And since the one carbon double bond O is also there, so oxo group is there. So these are all oxo acids. And since they are oxo acids, and what we know, the alkali metals, they are, and they are oxides, and they are metals, and they are hydroxides as well, they are all basic in nature. And these oxo acids are acids. So base and acids, when they react, they will form the salt. And the salt that we obtained while reacting oxides or any other compounds, and their alkali, pure alkali metals with the oxo acids, and the salt that we obtain is called the salts of oxo acid of the alkali metals. And so the alkali metals form salt with all the oxo acids because they are all basic. These metals are, all the metals, they are basic in characters. They can easily provide electrons, and this basic character. So what means basic character means what? These metals, they have only one electron, though these electrons have they try to give these electrons into the during the reaction. And this electron donating tendency is what you can consider. Electron donating tendency means the interacting with electron rich species. So they can very easily interact with the electron uh, donating species or electron rich species. Another way you can think of the alkali metals, they can form the cation very easily. So that cation will be electron deficient, and that cation can easily interact with the anion of the oxo acids. So they form salts. So these salts are generally soluble in water and thermally stable. So these salts of alkali metals, oxo salts of alkali metals, they are usually soluble in water and they are also thermally stable. Thermally stable means they, if you heat them, they will not easily be decomposed. They may be decomposed at very high temperature, but usually they are stable. This is what the thermal stability means. So there are carbonates. Carbonates means this carbonic acid salt of alkali metals with the carbonic acid. So this carbonate will be here. You can see carbonic acid H2CO3. If at the place of H2 I write Li2CO3 or Na2CO3. So the M2CO3, the carbonates, and in most cases the bicarbonates are all highly stable to heat. Not the lithium has some other properties. So lithium, usually most of the metals we see they are thermally stable. As the other than the carbonates, if you look at the lithium carbonate is not thermally stable. We have seen it earlier, but rest of the carbonates are thermally stable. They are easily dissolved. As the electropositive character increases down the group, the stability of carbonates and bicarbonates increases. The stability of bicarbonates and carbonates will be increasing with the increasing electropositive character down the group. So lithium carbonates is not so stable to heat. As I have said, lithium being very small in size polarizes a large CO3 2 minus means the carbonate ion, leading to the formation of more stable lithium oxide and CO2. And its bicarbonate of lithium does not exist as a solid. And we have seen it, it exists as a liquid. So it doesn't form the solid crystalline compound. Now so this basic property, that basic chemical property that we have summarized of the chemical compounds of alkali metals. Now let us look into the anomalous properties of lithium. Anomalous properties of lithium now is what we have seen, that the lithium many times its properties depart from the usual properties of the alkali metal compounds or alkali metals, their behavior itself, the chemical reaction and the stability of the chemical compounds, their solubility, they're related to lithium, they are all much different than the rest of the alkali metals. So let us see few anomalous properties of lithium. So first is what they say on the physical properties. Lithium is much harder than the other alkali metals. And why it is harder? If the why a certain compound is harder? Because if the bonding between any elementary particle that makes that substance, if their bonding is very strong, so that substance will be harder, and that is why this carbon diamond is why it is harder, because there is the formation of carbon carbon bond, and all this is the long chain, and the carbon carbon bond is very stable bond. Its thermodynamic stability is very high. It's mean a lot of energy is released during the formation of this bond. So what we see, the diamond is very harder. Similarly, what we see in the case of alkali metals, lithium, the metallic bonds are formed in the pure metals. If you look at all the pure metals of alkali metal group, means the first group, that these pure metals, the metallic bonding in the lithium is strongest. And why it is strongest? Because if you know the metallic bonding, the basic nature, main nature, what we have seen earlier is the basic. I should avoid because we have the basic and acidic character we are looking. Basic now is the fundamental property. So lithium is a smaller in size. In the metallic bonding, what we see that there is a cation, metal cation, and the valence electrons are there, and these valence electrons are there, and they are released. So there is the formation of the cation, and the electrons are there, and so these electrons can interact with the many cations, and the many cations will be interacting with the main, and one cation will be interacting with the many electrons in different direction, and one electron will be attracted by many cations. And so this is a way you can say, though LICL kind of formation, this bonding is there, but its structure is a bit different, because anyway this electron is a part of the atom itself. So metallic bonding, it appears because of the cation in attraction between cation and its valence shell electron. If the cation size is smaller, so one can expect that this attraction will be more between cation and the electron, and if that is more, so what we will see, the metallic bonding will be stronger. And so lithium cation being the smallest in size, it forms the strongest metallic bonding, and so the lithium is harder than other alkali metals. And since this metallic bonding is stronger in the lithium, so what we'll see, its melting and boiling points are also higher than other alkali metals. So lithium, another thing is lithium. We know the lithium is lightest atom. So atom is its mass is only, atomic mass is around 7. Mass number is 7. After lithium, the sodium is 11. So not sodium is 23. Sodium is 11 is the atomic number, and lithium atomic number is 3. So mass number is 7. And now the sodium with lithium 7, sodium 23, potassium 39. You can look at the mass number. So mass number of other alkali metals is much high. So each atom is much heavier, and because of that, what happens, in the same volume, the density usually increases down the group. And so lithium is, their density is least because of the atomic mass is least among the group metals. So lithium is what? It is the lightest atom. A lightest means the lightest here means the density we correspond to, and the density of lithium that we know only 0.53 gram per ml. It's almost half of the density of water, because we know the density of water is around 1 gram per ml, and the density of lithium is only 0.53 gram per ml, so almost half of that. And so lithium, what we have seen earlier is, we have studied that the alkali metals usually they are kept in kerosene. However, we do not store lithium in the kerosene, because what happens, if you put lithium in kerosene and the density of this lithium is much less than the kerosene, so it will what? It will float on the kerosene. Lithium will float on the kerosene, so it will come into the contact of oxygen, so it will react. So we do not store lithium into the kerosene, because kerosene density is 0.8, lithium density is 0.5, so it will come and float onto the surface, and then it will be exposed to oxygen and will react with oxygen to form oxide. So what do? We store it in the paraffin wax. So paraffin wax is actually wrapped around the lithium, whatever the lithium rod or salt, that a small block of the lithium that we keep, we try to store, we wrap those things with the paraffin wax, and that is why how it is, that is how it is stored. So lithium is least reactive. This we have also seen, lithium is least reactive, but the strongest reducing agent. Why it is least reactive? Because its ionization potential is highest. So its electropositive character is least, ionization potential is highest, so it is least reactive. However, if its reactivity towards the reducing property is maximum among all the alkali metals, and why not only the alkali metals, its reducing property is highest among all the elements that are there in the periodic table, and that we can see into the electrochemistry when we are. So why it is? Because lithium's hydration energy is very more. So whether it will in the solution, when we look at the reducing property, we are talking about this into the solution, aqueous solution. And the aqueous solution, lithium ion, its hydration is very facile, and because of the strong hydration, so what we see, the lithium plus formation is more vigorous. So lithium plus ion into the aqueous solution is most stable among all the other alkali metals. So when its size becomes larger because of the high extent of hydration. So lithium, though it is least reactive, so its reactivity towards other reactions is least, but it's the strongest reducing agents among all the elements of the periodic table. Here we are comparing with only alkali metals, so we are comparing it for the alkali metals. When heated in ammonia, lithium forms imide. This is another property of lithium that departs from the alkali metal. So lithium forms imide. The amide that you know, usually there are two amides. And the carboxylic acid amide, when we study it in the organic chemistry, carboxylic acid amide is what? The carboxylic acid is a derivative of carboxylic acid. The carboxylic acid is RCOOH group. Now, if you just replace this OH, last OH group, with NH2 or NHR or NHR2, NR2 or NHR or NH2, anything, So what we'll get, this is the carboxylic acid amide. However, in normal amide, when we talk in the inorganic chemistry, we see this NH2 minus group we also called amide. NH2 single minus, anion is amide, and the imide is what? If you replace two hydrogens, the ammonia is there. If from the ammonia you remove one H plus ion, so what will be the left is what will obtain is amide. So if you remove two H plus ion from ammonia, we will get imide. So the lithium usually forms imide. So imide means this is NH2 minus. The two hydrogens from the ammonia is removed. Two hydrogen, not hydrogen, two protons from ammonia is removed. So two negative charge on the NH minus will be there, and that two negative charge or two minus is actually balanced by two Li plus ions. So that is why it is Li2NH. So lithium forms Li2NH. It forms imide. The other alkali metals, they forms amide. They form MNH2. M means that this M is here sodium, potassium, rubidium, and cesium. When burnt in air, lithium forms mainly normal oxide that we have seen, Li2, and some LiO2 that is not important. However, sodium forms peroxide, and other alkali metals form superoxide that we know. So lithium's property is also different here. You can see here the sodium's property is also a bit different than the other list of the alkali metals. But what we see, the mostly the lithium, in the most of the cases, lithium's property is much different than all the alkali metals. And so lithium oxide, lithium Li2 is less basic, and this is less basic because no, the electropositive character is less and less soluble in water than other alkali metals. This one property. So lithium again departs, their properties departs from the other alkali metals. Li2O, wow, it is less basic lithium oxide, normal oxide, and it's less soluble in water than other alkali metals. Lithium is the only alkali metal which directly reacts with the nitrogen. This reaction we have seen. Lithium is the only alkali metal which can directly react with the nitrogen of dry air to form lithium nitride. A lithium nitride, the chemical formula is N3 minus. So lithium nitride will be what? Lithium cation with single charge, so it will be, and nitrogen has 3 negative charge, so 3 lithium cation or lithium ion will be required to balance the charge of one nitrogen. So this is the compound that we form Li3N. So anyway, in the case of valency, we just interchange the valencies to write the chemical molecular formula. That is one thing. So lithium reacts with water slowly at room temperature. This is what we have also seen earlier. So lithium reacts with the water slowly with the water at room temperature. The reaction of sodium is vigorous. However, reaction of other alkali metals is violent with the water. So other alkali metals like potassium, rubidium, and cesium, they violently react with the water. It means almost the explosion. However, the sodium reacts vigorously, and the reaction of lithium with the water is slow. Lithium is weaker base. Lithium hydroxide is weaker base. I have explained it. So it's weaker base. However, other alkali metal hydrides are a stronger base. The sodium, potassium hydroxide, etc. So similarly, you can say rubidium hydroxide and cesium hydroxide. They are much stronger base than LiOH. And the other thing, these bases, they do not decompose so easily on heating, but the lithium hydroxide, it's easily decomposed on heating. So lithium hydroxide, when on heating, it forms lithium oxide, and water molecules will release. It will be released as a water vapor on heating. So lithium hydroxide decomposes to form lithium oxide on heating. However, other alkali metals of hydroxides are usually thermally stable. Unlike other alkali metals, lithium forms ethynide on reaction with ethane. So what we have seen that the lithium, we have also seen earlier, the lithium usually forms lithium lithium do not form lithium ethynide. However, other alkali metals, they form the metal ethynide in the case of the one reaction that we have seen with the potassium. So that ethynide means the lithium doesn't react with the acetylene. So lithium, the acetylene, ethane. Ethane is what? The acetylene. The acetylene, lithium do not react with the acetylene. However, the other alkali metals, they react with the acetylene or ethane. and so they form ethynide. Ethynide, why ID? Because we write the nitride, oxide, hydride, ID for the being negative ion, the anionic in nature. So this is ethine. This anion comes from the ethine, so we call it ethynide. So this is actually C2 2 minus. C2 2 minus is ethynide. So a metal reacts the alkali metals and all the four other than lithium, the sodium, potassium, rubidium, and cesium, they react with the acetylene to form metal ethynide, and the hydrogen gas is released during this reaction. For example, if it is a potassium, so this is a 2K plus acetylene, it will be KCCK, or you can write also K2C2 or M2C2. Lithium reacts with bromine slowly. The reaction of other alkali metals with bromine is fast. This is another departure from the usual behavior of the alkali metals, departure of the lithium's behavior. So the lithium reaction with bromine is slow. With the other alkali metals, it is fast. Similarly, lithium chloride is deliquescent. Deliquescent means it tends to melt or it tends to dissolve. So lithium chloride, it melts very easily and it forms, it crystallizes a hydrate. So lithium, it forms lithium chloride, it absorbs water from the atmosphere also, and it forms LiCl2H2O, this coordination compound it forms. However, other alkali metals, they do not form, they are not deliquescent in nature, means they do not tend to melt or dissolve. But the crystals of NaCl, KBr, or Ki, etc., do not contain water of crystallization. So, water of crystallization that we see, the lithium chloride, it contains the water of crystallization. Then, however, the crystals of other alkali metals, halides, they do not, or the chloride, bromide, and iodide, they do not contain water of crystallization. So they do not mean their crystals do not contain water. So their affinity with the water is decreased. They are not hygroscopic in nature. The lithium nitrate, when heated, gives lithium oxide. This we have seen. However, lithium nitrate, it gives lithium oxide, but other alkali metals, they get lithium nitride. And nitrate is NO3 minus, nitrite is NO2 minus. So lithiums, again, this is the departure from the usual group character, group behavior. So lithium nitride, it gives on heating, it decomposes to forms Li2O plus 4NO2 plus O2 is just valence reaction. These are other products that are formed. The lithium nitrate, when sodium nitrate, however, or the potassium nitrate or the rubidium nitrate, they forms nitride. They do not decompose completely. They only one oxygen atom is removed from this nitrate into the form of oxygen. So two nitrate, they form two nitrite and one oxygen molecule. Lithium sulfate do not form alum like other alkali metals. So alkali metals, we see usually alkali metals, this I have also described earlier, the lithium, other than lithium, all the sulfates of alkali metals, they forms alum. So lithium bicarbonate or lithium hydrogen carbonate is liquid while other metal bicarbonates are solid. This we know. Only lithium carbonate decomposes on heating. This is a property that you have also seen. Just to summarize it, the lithium carbonate on heating, it gives Li2O and CO2. The lithium carbonate is less stable. Why? Because of the smaller size of lithium atom. The polarization of the oxygen atom that is nearer to the lithium and is more, and so the oxygen and CO2 groups, they depart, they get separated, so lithium is less stable. However, other carbonates of other alkali metals, they do not decompose on heating. The lithium carbonate, lithium oxalate. What is the oxalate? Oxalic acid, you might have heard, H2C2O4. So once the salt of lithium salt of oxalic acid is the lithium oxalate. Lithium oxalate, lithium fluoride, lithium phosphate, that we know, they are the only alkali metal salts which are insoluble or sparingly soluble in water. The rest of the alkali metal salts are readily soluble in water, and readily soluble in water. What we see, all these salts, all these salts belong to the lithium only, which are sparingly soluble in water. Other, for example, the cesium iodide we have also seen, but there are only few such exceptions. The lithium Cl and LiNO3 having significant covalent characters. So why the LiCl and LiO3, they have significant covalent character, and that we know because of the smaller size of lithium, are soluble in alcohol and some other organic solvents. Some other organic solvents that we have seen, the acetal, ethyl acetate, and acetone. The pyridine, lithium chloride, is also dissolved in pyridine. These salts of the alkali metals are, however, that means they are dissolved in organic solvents like alcohol and pyridine, and so, but these salts of other alkali metals are not soluble in organic solvents. Because why? Organic solvents usually have less polar character. They are, if either they are non-polar, or if they are polar, their polarity is much less than the water. And the other alkali metals, what we see, they are more polar than the lithium salts. The other alkali metal salts are more polar than the lithium salts. So what we see, the lithium salts usually they are more dissolved in organic solvent, because we know the like dissolves like, less polar dissolves less polar, more polar dissolves more polar, or non-polar dissolves non-polar. So like dissolves like, that reason is there. And the reason behind the anomalous behavior of lithium is what? It's a very small size, that we know it's a very small size, and of the lithium ion, lithium metal and lithium ion both. And also because of very small size, but we see the polarizing power of lithium is more, and which results in increased covalent character. So if the polarizing is smaller size, polarizing is power is more, so it results in the greater covalent character of the compounds of lithium and compared to the other alkali metals. And also what we see, the lithium also do not have vacant d orbitals. All the alkali metals, if you look at from the sodium, we see the vacant d orbitals are there, because from the sodium the third period starts, and from the third period we see the availability of the d orbitals. And how do we know? Because as soon as you go to the third period, value of n is 3, and the value of n, the principal quantum number, is 3. So the possible azimuthal quantum numbers will be from 0 to n minus 1. So 0, 1, 2. N minus 1 means 3 minus 2 is, say 3 minus 1 is 2. So 0, 1, 2, all the numbers, whole numbers. So 0 belongs to s orbital, 1 belongs to p orbital, and 2 belongs, value of L equals to 2. This belongs to d orbital. So from the third period onwards, all the elements, they do have vacant d orbitals. Or even the filled d orbitals, they do have existence of d orbitals. Since the sodium, potassium, they all have vacant d orbitals, because we see the vacant last orbitals, the d orbitals, they are not filled by electrons. So they do have vacant d orbitals. However, in the case of lithium, the electronic configuration is 1s2, 2s1. So 2s1, the value of n, the principal quantum number, is what? 2. And for the 2, what are the possible azimuthal quantum numbers that belonging to it is 0 and 1 only. And why only up to 1? Because it goes up to n minus 1, and 2 minus 1 is 1. So from 0, 1, 0 belongs to S, and 1 belongs to P subcell. So no P subcells, so no P or so P subcells, no D subcells, so no D orbitals, no vacant d orbitals. So lithium also do not have d orbitals, and because of the availability of d orbitals, but we see there are many other chemical property that changes. Now what we see, as we see the lithium's behavior, its departure from the and its compounds properties, it departs from the properties of the other alkali metals, but what we see, its property is much closer to the properties of the magnesium, and this we call the diagonal relationship. So due to its small size, lithium differs from other alkali metals and the regions that we have seen, but resembles with magnesium as its size is closer to the magnesium. If you look at the lithium cation, size is 1.34 angstrom, Li single plus, and magnesium it is 1.3 angstrom. So they are quite closer to each other. So it resembles with the magnesium, and this is called the diagonal relationship, because if you look at the periodic table, the magnesium is diagonally opposite to the lithium in the periodic table. If you remember, you can imagine the periodic table, and there how where they are located in the first and second group. The similarities between magnesium and lithium that we can see. So both lithium and magnesium are harder and have higher melting points than other metals of their groups. Due to covalent nature, chlorides of both lithium and magnesium are deliquescent. Deliquescent, that means we know that it melts away in the process of decomposition. So this is what melts, and it also dissolves very easily. So and soluble in alcohol. So compounds of lithium, magnesium, the chlorides, their chlorides are also soluble in alcohol and pyridine and some other organic solvents, where chlorides of other alkali metals are not soluble in organic solvents. So we see the lithium's property is closer to the magnesium. So carbonates of lithium and magnesium decomposes on heating, and that we see, have seen the lithium, it forms carbonate on decomposition forms lithium oxide and carbon dioxide. Similarly, we see the similar reaction with the magnesium for the magnesium carbonates. So magnesium carbonates on heating decomposes to magnesium oxide and CO2. You should not be confused with the molecular formula because of the nature. 2 plus charge molecular formula is different, and so the stoichiometry may also differ in some cases. However, what we see, the nature of reaction, this also decomposes to form oxide, this also decomposes to form normal oxide. The rest of the things is all the balancing of the charge and balancing of the number of atoms. Hydroxides and nitrates of both lithium and magnesium decomposes on heating to give oxides, and this is what the nitrate, we have seen the lithium nitrate, it decomposes to give lithium oxide. However, other alkali metal of nitrates, they give nitride. So lithium nitrate, it gives lithium oxide. And similarly, what we see, the magnesium nitrate, it also decomposes to give magnesium oxide. And the NO2 gas, nitrogen dioxide and oxygen gases are released in both the cases. Similar reactions we also see for the lithium hydroxide and the magnesium hydroxide. Similar reactions do not happen for the other alkali metal hydroxides. So lithium hydroxide, what happens, it also decomposes to lithium oxide on heating and the water molecule. This reaction we have seen. The similar reaction with the magnesium hydroxides we also see. Like lithium hydroxides, magnesium hydroxides are also sparingly less soluble in water. So it also on heating it forms MgO plus H2O. The same oxide of these two metals are formed, and these are formed because of the decomposition of their hydroxides and nitrate. So hydroxides of other alkali metals are stable towards heat, while their nitrates give O2 and nitride, that we know. The hydroxides of other alkali metals are stable, this we have seen, and the nitrates give nitrite and oxygen. Both lithium and magnesium, they combine directly to nitrogen. What we have seen, lithiums only react with the nitrogen. Our other alkali metals do not react with the nitrogen, the gaseous nitrogen. But the magnesium we see, though it belongs to the other group, second group, but magnesium reacts with the nitrogen to form magnesium nitride. And what we see here, the chemical formula, it's in their nature is different, but they are all nitrides. Both the nitrides are decomposed by water to give ammonia. Both the nitrides of lithium and magnesium, when they react with water, they give ammonia and the hydroxide. So water means the lithium nitride, when it reacts with water, what does it do? So these hydrogens go with the nitrogen and lithium. Also, the one hydrogen from each water goes to nitrogen to form ammonia, and 3 OH groups will be there, and so on. It will form 3 LiOH. This is Li3, so reaction is balanced. Now the similar reaction, the magnesium nitride will write Mg3N2. Why? Because the valency of magnesium is 2 plus on is 2, and valency of nitrogen 3 minus 3, and their valencies will be interchanged while writing this chemical formula. So Mg3N2 is the chemical formula of magnesium nitride, and magnesium nitride on reaction with the water, it gives magnesium hydroxides that you see. Lithium also gives lithium hydroxide plus ammonia. Ammonia is formed. Although the chemical this is changed, and because of this chemical formula, though the similar compounds, that stoichiometry, these 8 molecules are there, stoichiometry also changes, but what do we see? The same reaction happens, and again the stoichiometry that we see to balance the total number of atoms. Why? Because we have to follow the law of conservation of mass, and the law of conservation, this balancing, we have just balanced the reaction. However, the basic reaction is same. Lithium nitride plus water gives lithium hydroxide plus ammonia, and magnesium nitride plus water gives magnesium hydroxide plus ammonia. Both lithium and magnesium combine with carbon on heating, that we have seen for the lithium, and a similar thing we see for the magnesium as well. So lithium and reacts with the carbon to form lithium carbide. So lithium plus carbon 2C we can write, and forms LiC2. Similar reactions that we see, magnesium 2 magnesium plus 3C, this is a carbon. And the carbon is, you can use the coke or the graphite, and it forms also carbide, and carbide's valency is 2, that we have seen in the molecular orbital theory. The valency of carbide also, it was not explained by the valence bond theory, we explained it from the molecular orbital theory. So carbide's valency is 2. So 2, it forms Mg2C3. This is the magnesium also forms carbide, like the lithium forms carbide. However, other alkali metals do not react with carbon to form carbide. Only lithium reacts with carbon to form carbide. So here the property of lithium departs from the alkali metals, but it resembles to the property of magnesium. This is called, we call the diagonal relationship. Bicarbonates of lithium and magnesium are more soluble in water than carbonates, whereas carbonates of alkali metals are more soluble. So my bicarbonates in the, for the lithium, the bicarbonate is more soluble, and other alkali metals carbonate is more soluble. And the similar thing that we see for the magnesium as well. Magnesium bicarbonate is more soluble than magnesium carbonate, and its property is more closer to the lithium, or the lithium property is similar to that of the magnesium. The periodic properties of lithium and magnesium are quite comparable, and the periodic properties in the periodic, all these properties that you can see, they are also comparable. Both have high polarizing power. And why they have high polarizing power? Because charge to size ratio is high in their cases, in both the cases of lithium and magnesium. So they have high, and their polarizing power is quite high, or much higher than the other alkali metals. The lithium and magnesium form only monooxide on heating in oxygen. So monooxide, as we see, lithium forms oxide or monooxide. So lithium it reacts with oxygen to form lithium oxide. Similar thing with magnesium also forms oxide, and its formula is MgO. I mean, the pure metal when it is heated with the dry oxygen. Lithium sulfate, like magnesium sulfate, does not form alums. So lithium sulfate and magnesium. Lithium sulfate doesn't form alum. So what we see, however, other alkali metal sulfates, they form alum, and the similar to the lithium. And this property of lithium sulfate not forming alum is resembles to the property of magnesium sulfate. The bicarbonates of lithium and magnesium do not exist in the solid state. That for lithium, we know we have I've explained, and a similar thing we see for the magnesium as well. So magnesium bicarbonate also do not exist in the solid state. It exists in only the solution or the liquid state. So the lithium chloride and magnesium chloride both are deliquescent and separate out from their aqueous solution as hydrated crystals. So magnesium chloride and lithium chloride, when you dissolve them in water, and they will be separated out at in the crystals, they forms their crystal with the water of hydration, two water molecules as a water of crystallization. LiCl also contains two water molecules as the water of crystallization, and MgCl2 means magnesium chloride also contains two water molecules as the water of crystallization. I think now here I'll stop. Other things, the important compounds and their properties, how are they formed, these things that of the alkali metals, particularly related to sodium, that we will see in our next class. And then there will be this. Yes, this portion will be over. This portion is the portion related to this alkali metals will be over.